Welcome to the deep dive. Today, we're jumping into something really central to modern AI, large language models or LLMs. These models are everywhere now, writing code, helping with emails. It's quite amazing. And the core of that power, it's this thing called the attention mechanism. It's kind of the magic behind how they understand context. But, and this is a really big but, they have huge demands. Memory, computation, it's significant. A lot of that comes down to the key value cache, the KV cache. And it's not just a small issue, it's a genuine bottleneck. It makes it really tough to use LLMs for tasks needing long context, like summarizing a whole book or even just running them on your phone. It limits where they can go.
That's exactly right. And it's why the paper we're digging into today is so interesting. It's titled GTA, Grouped-Head Latent Attention. We're going to follow its structure pretty closely, almost like an academic review, starting with the problem they identify, moving through their proposed solution, the method, and then looking hard at the results and conclusions. Our mission here is to really understand how they claim to get these big efficiency gains without hurting performance. It's about trying to break a long-standing trade-off.
Okay, so let's start there with that core problem.
Yeah.
The attention mechanism, you said, it's like how the LLM focuses.
Exactly. It lets the model weigh the importance of different words or tokens in the input. This idea, from Vaswani and others back in 2017 was foundational, super powerful.
But incredibly demanding. That KV cache, it's like the model short-term memory for context, right? And it just grows and grows.
Precisely. It scales with the length of the input sequence. So for long documents or long conversations, the memory and compute needs just explode. This really limits things in the real world. Anywhere memory or speed is tight, like you said, your phone, or maybe embedded systems in cars, things like that.
Right, so people have obviously tried to fix this before.
Oh, definitely. There have been quite a few approaches. The standard is multi-head attention, MHA, works well, but that KV cache scaling is the problem. Then came multi-query attention, MQA. The idea there was, okay, let's just share one KV set across all the attention heads.
Saves a lot of memory, I bet.
A ton.
Yeah.
But the downside is you lose expressivity. All the heads are looking at the same limited memory, so they can't capture as much nuance.
Okay, so MQA was maybe too extreme on the saving side.
Sort of. So then grouped query attention, GQA, came along. It groups the heads and shares KV pairs within those groups. It's a balance.
The compromise, yeah.
Yeah.
It's used in some big models, right?
Yeah, like Lemma. It's a decent middle ground, but you're still trading off some attention granularity. And there are others too, like Multi-Head Latent Attention, MLA. That tries to compress the KV cache into a smaller latent representation.
But that has its own issues.
Yeah, MLA can have high computational overhead during that compression and decompression. So the pattern was, well, you optimize one thing, memory or computation, but you often sacrifice performance or another efficiency aspect. The big question remained. Could you actually improve memory, computation, and keep the performance high all at once? Could you have it all?
That really is the million-dollar question. Because it always seemed like you had to pick your poison. And this is where GTA makes some, frankly, pretty bold claims. This paper says GTA reduces self-attention computation by up to, 62.5%?
62.5%, yeah. And the KV cache size reduction is claimed up to 70%.
Wow. Okay. That sounds almost too good to be true. And they say it matches or beats GQA performance across different model sizes.
That's the claim. From 160 million parameters up to a billion. Plus, they report 2x throughput in inference compared to GQA.
2 times faster.
Okay.
They're framing it as more than just one technique, like a design roadmap.
Exactly. They think this approach points the way forward for efficient attention mechanisms in general.
So how? How do they think they crack this trade-off? Let's get into the how.
Okay. So GTA builds on existing ideas, as most research does. The paper positions it relative to 2 main lines of work we've touched on. First, those shared KV cache methods. We talked about MHA, infinite KVs, high memory, MQA, single shared KV, low memory, less expressive, and GQA, grouped sharing, the balance. There are others too, like YOCO, which shares KVs across layers, but all of them face that core challenge, trading expressivity for efficiency. GTA aims to overcome that trade.
And the second category?
Latent attention mechanisms, like MLA, which we mentioned, or PLM. These compress keys and values into a compact latent vector, saves memory.
Right. How does GTA differ from those?
This is really the crux of it. GTA uses a compressed latent value representation, yes, but it combines it with a very specific nonlinear decoder. This decoder is inspired by things like gated linear units, GLU, or gated attention, GLA. It dynamically generates the full head-specific value representation from the compressed one.
Dynamically.
Yeah.
So it rebuilds the value information on the fly for each head.
Exactly, using that nonlinear function. This combination is key. It allows them to keep the expressivity high, even with the compression, and do it with low computational cost. It packs more information density, you could say.
Okay, so let's really unpack that mechanism. The paper walks through it step by step, right? Starting from MHA.
It does. It revisits MHA, then introduces two intermediate concepts, GVA and GHA, before getting to the full GTA. It's a nice way to build up the intuition.
Let's do that. Quick MHA recap. Q, K, V.
Right. Multi-head attention. You take your input, project it into queries Q, keys K, and values V for each attention head. The query is like asking a question about the context. The keys are like labels for the potential answers. The values are the answers or the information content. You compute attention scores based on how well queries match keys and use those scores to weigh the values. That gives you the output.
And the problem is storing all those Ks and Vs for every head, for the whole sequence length. That's the O2HN scaling issue.
Precisely. That's the bottleneck for long sequences.
Okay, so what were the stepping stones? GVA first.
Grouped value attention, GVA. Here, they share the attention weights the scores calculated from Q and K across groups of heads. This saves computation because you calculate fewer attention patterns. But each head still projects its own distinct values, so the memory cost for the values is still relatively high.
Got it. Shares the attention pattern, but not the values themselves. What about GHA?
Grouped head attention, GHA, goes further. It shares the query and key representations, Q and K, within groups of heads. This reduces compute and storage more because you have fewer unique Qs and Ks, but...
There's always a but.
Yeah. The potential downside is reduced diversity in the queries and keys. This might limit the model's ability to pick up on very fine-grained details in the input.
Okay, so GVA save compute, GHA save compute, and some storage, but maybe lost some precision. How does GTA build on this?
So GTA starts differently. It computes the queries Q and keys K, but instead of full values V, it computes a compressed latent value representation called C, directly from the input.
C for compressed.
C for compressed, yeah. This C is much smaller than the full set of Vs would be. It's the efficient representation that gets stored.
Okay, but you need the full values eventually, right?
You do. And this is where the magic happens. The nonlinear value decoder. For each attention head, GTA dynamically generates a full value matrix, let's call it VI for head I, from this shared compressed C. It uses two things, a projection matrix specific to that head, and crucially, a nonlinear gate. The paper uses a sigmoid function applied based on the current token's own representation.
Whoa, okay, so that nonlinear gate, it's filtering or adapting the compressed C based on the current context, specifically for each head.
That's a fantastic way to think about it, like a context-adaptive filter. You have this compact library, and the gate lets each head instantly customize the information based on the immediate need, adding nuance.
That sounds really clever. It avoids just having a blurry, compressed view by adding back specificity right when it's needed.
Exactly. The paper calls this full-rank projections. It avoids the information loss you might get from simple linear compression. It boosts the diversity of the outputs across heads, which helps maintain performance.
And how does this play out for efficiency, especially during inference?
That's where it really shines. During inference, you only need to cache the keys, K, and that compressed latent value, C. That's a huge memory saving compared to caching K and the full V for every head like an MHA or even the grouped Vs in GQA.
And the nonlinear decoding part, does that add a lot of cost?
It adds some computation, but it's done on the fly for the current token. The paper argues this overhead is minimal compared to the massive savings in memory bandwidth and storage from the compressed cache. So GTA strikes this really nice balance. Scalable memory via the compressed cache, expressive power via the dynamic nonlinear decoding, and overall computational efficiency.
It's aiming for that sweet spot.
Okay. The design sounds elegant, hitting those goals of scalability, expressivity, and efficiency. But theory is one thing. Did it actually work in practice? Let's talk about the performance evaluation. The proof is in the pudding, right? Absolutely. And they ran extensive experiments. Their methodology seems quite solid. They trained standard transformer models using the C4 dataset, testing with sequence lengths of 2048 and 4096 tokens. And here's a crucial detail, something you really appreciate in careful research. They kept all the non-attention parameters fixed across the models they compared.
Meaning things like the size of the feed-forward layers, the hidden dimensions?
Exactly. Everything else was held constant. So when they compared GTA against MHA, GQA, and MLA, any differences in performance could be confidently attributed just to the attention mechanism being tested.
That's good scientific practice,
Yeah.
isolating the variable. So what did they find? Let's start with the smaller models, maybe 160M parameters.
Right. So for the 160M models, using a 2048 token sequence length, one configuration of GTA actually showed lower evaluation loss, meaning it learned better and better perplexity on the Wikitext benchmark than all the competitors, including GQA.
Lower loss and better perplexity. That's impressive.
And another GTA configuration achieved higher accuracy on downstream tasks.
And this was with the reduced memory.
Get this. This performance was achieved using only 12.5% of the KV cache size that MHA would use for the same configuration. Just 192 dimensions compared to 1536.
12.5%. That's an enormous saving for comparable or even better performance. What about longer sequences, 4096?
Even at 4096 tokens, GTA remained very competitive, holding its ground against the others while still offering those memory savings.
Okay, how about bigger models? 500 IMR parameters.
Similar story, really. The trends held. Lower evaluation loss for GTA, higher accuracy on tasks, competitive perplexity scores, and again, achieving this with just 12.5% of MHA's KV cache size, 320 dimensions versus 2560. They even showed comparable results using just 7.5% of the cache in some configurations.
Wow. Okay, do they do any ablation studies, like tweaking parts of GTA to see what really matters?
Yes, and those were quite revealing. First, they tested sharing the attention matrix across heads. You might think making things more shared would hurt performance.
Yeah, intuitively. Less specialization per head.
Right. But counterintuitively, sharing the attention matrices actually slightly improved performance in some cases, while also reducing the total number of model parameters.
We improved. How?
The author suggests it might act as a form of regularization. It implies that standard MHA might actually be over-parameterized in its attention matrices, and sharing helps prevent overfitting.
Huh. Interesting. What else did they test?
They looked at the effect of head dimension, basically, how much capacity each head has. As expected, increasing head dimension improved performance for both GQA and GTA. But GTA consistently outperformed GQA at equivalent head dimensions, showing that its combination of head capacity and the latent value approach is effective.
And what about that crucial nonlinear gate? Did the choice of function matter?
It mattered significantly. They tested the sigmoid function against sparser alternatives like CLU, Swish, and ReLU squared.
Yeah.
The sigmoid consistently performed better. The sparser activations actually hurt performance.
That is surprising. Usually sparsity is considered good in neural nets, right? Helps with efficiency, prevents co-adaptation.
Often, yes. But here, the authors found that sparsity seemed to reduce the effective rank or richness of the generated value representation. It degraded the expressivity that the nonlinear gate was supposed to provide.
So for this specific architecture, density in that gate was actually key. Why this behaves differently?
That's a really interesting question for future research, isn't it?
Absolutely. It highlights that intuitions from one part of deep learning don't always transfer directly to another. Architectural choices interact in complex ways.
Okay, so impressive results on smaller models. Did they scale it up further, like to 1 billion parameters?
They did. They trained a GTA-1B model on a huge dataset, 220 billion tokens. And the efficiency numbers are stark. GTA-1B used only 30% of the cache size compared to a GQA-1B model, and only 37.5% of the self-attention computational cost, FLOPs.
30% cache, 37.5% compute. That's massive savings at the billion parameter scale. How was the performance? It achieved comparable performance to the GQA-1B model, both in the base pre-trained model and after fine-tuning on a dataset called Tulu-3. In fact, after fine-tuning, GTA-1B showed a noticeable improvement in average accuracy across tasks.
And again, the rest of the model architecture was the same, only the attention mechanism differed.
Exactly. The MLP design, everything else was kept constant. So these gains, comparable performance with drastically less compute and memory, are directly attributable to the GTA mechanism itself.
The performance data looks really strong then. It seems to live up to the claims. What about the raw efficiency numbers? And maybe more importantly, how does it perform in actual deployment scenarios?
Right. They broke down the efficiency both theoretically and empirically. The theoretical analysis confirms the math behind the savings. That KV cache reduction from O2HN and MHA down to O NKDH plus NCDLN for GTA, that's where the math for the up to 70% reduction comes from.
Where stink is number of key groups, acting to the latent value dimension.
Exactly. And similarly for self-attention computation FLOPs, a significant reduction compared to MHA. And yes, GTA adds that bit of linear computation for the nonlinear decoder, but the paper argues this trade-off is highly favorable, allowing it to get near MHA expressivity with efficiency closer to simpler methods like GVA-GHA.
Okay, theory checks out. What about benchmarks on real hardware?
They used a framework called LLM Viewer to simulate optimal inference performance on high-end hardware, like NVIDIA H100 GPUs. The results there showed GTA-1B consistently outperforming GQA-1B in latency for both phases of inference. The initial prefill, which is compute-bound, and the token-by-token decode phase, which is often memory-bound.
Better latency in both compute and memory-bound phases. That suggests a really well-rounded efficiency profile.
It does, and they didn't stop there. They did practical inference deployments using the standard transformers library from Hugging Face.
Okay, this is closer to what developers would actually experience.
Exactly. And they tested across a really wide range of hardware, not just the top-tier H100s and A800s, but also consumer cards like an RTX 3060, Apple Silicon M2 chips.
Even Raspberry Pi, you mentioned that earlier.
Yep, even the BCM2712 chip from a Raspberry Pi 5, they really wanted to show broad applicability.
And across different precisions, like FP16.
Yes, full precision, FP32, and half precision, FP16, BF16. Across all these different hardware platforms and precisions, GTA-1B consistently maintained its performance advantages over GQA-1B. One interesting finding was how well GTA performed in memory-constrained scenarios, especially when using cache offload. That's when you move the KV cache from the super-fast GPU memory to the slower but much larger CPU memory to handle very long sequences.
Because GTA's cache is so much smaller to begin with, moving it back and forth is less of a bottleneck.
Precisely. Its efficient memory access patterns really shine when memory bandwidth is the limiting factor, making it very versatile for different deployment constraints.
So the overall picture from the efficiency evaluation seems really positive then.
Yeah, the conclusion is that GTA-1B delivers a strong, validated combination of memory efficiency, computational speed, and practical performance across the board.
Okay, let's try to wrap this up. Grouped-Head Latent Attention, GTA. It sounds like more than just an incremental improvement. We're looking at potentially massive cuts in compute up to 62.5% fewer FLOPs, and memory needs up to 70% smaller KV cache. And translating that into potentially doubling inference speed on real hardware without apparently losing model quality, that feels pretty significant.
It really does. It seems GTA successfully navigates that tricky trade-off between efficiency and expressivity that's been a major hurdle for LLMs. This could genuinely pave the way for more efficient LLM design and deployment, making these powerful models more practical in a much wider range of situations. Think data centers, yes, but also edge devices, which is really exciting. And the authors themselves point out there's likely still room for more optimization through further engineering. They see this as a stepping stone.
That's exciting too. So it leaves us with a final thought for you, our listener. With breakthroughs like GTA making LLMs so much more efficient, what new doors does this open? What applications, previously just too resource-hungry, might now become feasible? Think about that. How might advancements like this shape the future of AI, and who gets access to it? Definitely something to ponder.